This is just an experiment. Well, you're gonna be Are you videotaping right now? You're erasing the board? Well, did it even start? Maybe it didn't even start. Okay, now it's going. So you're gonna have to read me the problem since I have this. Okay, what's number 8? Is that the one with the square? Yeah. Is it pointing the right way? Okay, number 8. Okay, read me the problem. I kind of forgot it already. You have a square, I know. A, B, C, D. Point X is randomly placed inside square A, B, C, D. What is the probability that angle AXB is obtuse? Okay. Now, if you had a semicircle right there, and I put point X anywhere on this semicircle, isn't it going to form a right angle there? Why is it? We talked about that how many times in this class? Why is it when you have a semicircle, and that's the hypotenuse, why is it always going to be a right triangle? Because geometry. What kind of angle is this? What kind of angle do we call that? We call it an inscribed angle. An inscribed angle is always half of the intercepted arc. So if this is 80 degrees, that's going to be 40 degrees, right? That's from geometry A. Okay, so if you have, this is the diameter, that's a semicircle. Why is it when you draw this angle here, it's always going to be 90 degrees? Because that arc is 180 degrees. So half of 180 is 90. So that's why, if you have a semicircle right here, then if I put point X right on the rim of the semicircle, it's always angle AXB is always going to be a right angle. But we're looking for the probability that AXB is obtuse. Not a right angle, obtuse. You guys understand this? Okay, don't answer me again. As usual. So, if I want angle AXB to be obtuse, do I put it inside the semicircle or outside the semicircle? Because look, if you put it on the semicircle, it makes a right angle. We want it to be obtuse. That means bigger than 90 degrees. So where should point X be? Inside the semicircle. So point X has to be somewhere here. So if you randomly pick a point, what's the probability that it's going to be inside the semicircle? Well, don't you just go by area, right? Isn't it just the area of the semicircle divided by the area of the square? Yeah. So what do you want to call the radius of this semicircle? R, 1, 2, 1. Choose wisely. It doesn't matter. Okay, just pick R then. You could pick 1, but you want to go with R? Let's go with R then. Okay, so what's the area of that semicircle? It's half a circle. What's the area of a full circle? Pi r squared, but that's half. And then, if this is r and this is r, that means the side of the square is 2r, so what would be the area of the entire square? 4r squared. And then, the r squareds cancel out! Multiply top and bottom by 2, and you get pi over 8. That is the probability that if you randomly pick a point, then angle AXB will be obtuse. You know, this is just an experiment right now, you know. When we do it for real, which is going to be next week, it would be good if you had shown a little, like, maybe a little response now and then. Like, yeah, something would be nice instead of just. Question. You had your hand up?
Just waving to the camera.
Anybody else want to wave? Okay, are you sure that's the only question? Okay,
Yes.
you guys are good then. Okay, today we move on. Okay, what kind of problems do we have today? Oh, wait a minute. How come I see problems on here that every year they ask, but not period 3 this year? Okay, you guys are special, all right. Oh, and then we gotta also learn the birthday problem today, it looks like. Okay, here we go. I thought I combined these next 2 worksheets together, but I guess I didn't. So tonight's homework is going to be easy. Okay, let's say we have a jar. In the jar, I have marbles. Okay, what kind of marbles do I have? I have 4 blue marbles, 3 red marbles, and 2 green marbles. How many total marbles in the jar?
9.
Okay, now this is the kind of problems you get in pre-algebra, yeah? If I randomly pull out 1 marble, what's the probability that it will be blue? 4/9, right? If I were to randomly select 1 marble, what's the probability that it will be green? 2/9. You think we're going to have problems that easy in this class? No, moose breath. Okay? So, if I were to randomly select 2 marbles, what's the probability that both of them will be blue? Okay, so if I so this is what we're doing. I am going to randomly draw 2 marbles. What is the probability that both are blue? Okay, so we're going to do the probability by just drawing marbles one at a time. Okay, so how can I get 2 blue marbles? Blue on the first, blue on the second. This is the kind of probability that you guys did in biology, I believe, yeah? So, if I pull out a marble, what's the probability that the first one is blue? 4/9. That's easy enough. Now we have to decide, is this problem with or without replacement? Anytime you study probability, that's a phrase that's going to come up. With or without replacement. In other words, if I just pick out a ball, I look at the color, and then I put it back in the jar, and then I draw it again, what do we call that? That's called with replacement. The other one is without replacement. If I pull out 1 marble, I look at the color, I keep it out of the jar, and then I pull out another one. That's called without replacement. That's the more normal one, yeah? Okay, so if it doesn't say anything, you have to assume that it's without replacement. So without replacing it, notice that I took out a blue marble already. How many marbles are left in the jar?
8.
There's only 8 marbles left, and how many of them are blue?
3.
So after pulling out the first blue marble, what's the probability of now pulling out another blue marble? 3/8. And what do I do with these 2 numbers? You multiply. Why? Because they're close together, so you guys are learning. No, it's because of this. The probability of event A and event B happening is equal to the probability of A times the probability of B knowing that A occurred. Have you seen that before? It's the probability of event. So this is the probability of pulling out a blue marble on the first draw and pulling out a blue marble on the second draw. That's equal to the probability of pulling out a marble on the first draw, and then the probability of pulling out a blue marble on the second, knowing that you pulled out a blue marble on the first. That's what that means. So again, just like when we did combinatorics, this word and implies multiply. Okay, so is that the answer right there? Yes, that's the answer. All you have to do is simplify it. So again, just like the combinatorics test, if you write that down on your paper, you get 3 out of 4 points, and you want the 4th point, you gotta compute it. And please don't do this. 4 times 3 is 12, 9 times 8 is 72, and then you start reducing. Come on. Every year there's always clowns that do that. What do? Let the canceling begin. 4 goes into 8 2 times, 3 goes into 9 3 times, and so 1/6 is the answer. Oh, you guys think you're good now, yeah? Okay, I'm going to randomly draw 2 marbles. Find the probability of getting 1 red marble and 1 green marble. Okay, let's do a specific case. Pull out the red on the first and then a green on the second. What's the probability of pulling out a red marble on the first draw? 3 nines. Okay, let's just leave it 3 nines. Now that the red marble is out of the jar, what is the probability that the second draw will be a green marble? 2 out of 8. Multiply those 2 numbers together and that's your answer. Because that's not the only way you can get 1 red and 1 green marble. This is just the probability of getting a red on the first and a green on the second. Are there other orders I can get 1 red and 1 green? Yeah, I could have pulled out the green on the first and the red on the second. So let's do that case. Green on the first, red on the second. What's the probability of pulling out a green on the first? 2 nines. Once the green marble is out of the jar, what's the probability of pulling out a red on the second? 3 out of 8. And then what do I do with these 2 cases? You add them. But can you see that it's the same thing? Can you see the numbers are the same? So instead of doing that, a faster way would be, again, just like we did combinatorics, do a specific case, red on the first, green on the second, and then multiply by the number of cases. Yeah, so there's 2. Now that's the answer, and then now you just compute. Let the canceling begin. 3 goes into 9 3 times, 2 times 2 is 4, goes into 8 2 times, so the answer is 1/6. Yeah, that's the same answer. Okay, let's pull out 3 marbles now. So I'm going to randomly draw 3 marbles. I'm not going to write this on the board. Find the probability of you get 1 of each color. We're pulling out 3 marbles, 1 at a time now. Okay, so what's the probability? Okay, let's do a specific case. You pull out a blue on the first draw, a red on the second, and then a green on the third. What's the probability of pulling out a blue marble on the first draw? You gotta be joking.
4 nines.
Come on, practice for next week. At least say something. Nah. I'll take a bark or something. I'll take an animal sound. What's the probability of pulling out a red on the second draw? 3 8s, and then now a green. 2 7s. But is that the only order you can get 1 of each color? So now you have to multiply by the number of different cases or orders, yeah? So how many orders are there? How many ways can you arrange like 3 things in a row? 3 factorial, so you gotta multiply by 3 factorial, which is 6. I can leave the simplifying to you, right? Okay, again, I'm going to randomly pull out 3 marbles. What's the probability that I get 2 red and 2 green marbles? Except 1, because that would be 4. Okay, what's the probability of pulling out 2 red and then 1 green? Okay, do a specific case. Pull out a red on the first draw, a red on the second, and then a green on the third. What's the probability of that happening? Red on the first. 3 nines. Red on the second. 2 8s, and then now a green. 2 7s. But is that the only way I can get 2 reds and 1 green? No, so we need to multiply by the number of different orders, which is? How many 3-letter words can you make with 2 R's and 1 G? That's like Mississippi or alfalfa. 3 factorial over 2 factorial, which is just simply 3. So you need to multiply by 3. Or just think about it this way. The green one could have been here, here, or there. Right, and that's 3. So it doesn't matter how you count it, you just need to multiply by 3. So can you guys understand that when you pull out one at a time, there is an order to it? Okay. Okay, now let's do the same exact problems, except now we're going to do it with replacement. Okay, we're going to do all 4 of these problems again, except now with replacement. In other words, you're going to look at the marble, note the color, and then put it back in the jar. Okay, so what's the probability you get a blue on the first marble? 4 nines. Put it back in the jar. What's the probability of pulling out a blue marble again? 4 nines. And is that the only way you can get 2 blue marbles? Blue on the first, blue on the second? Yes, how about a nod of the head? Okay, so that's it. So the answer is just 16 out of 81. Hey, that's easy. Okay, now what about 1 red and 1 green? Okay, let's do a specific case. Red on the first, green on the second. What's the probability of pulling out a red marble on the first draw? 3 nines. Put the marble back in. What's the probability of now pulling out a green marble? 2 nines. But is that the only way you can get one red and 1 green? No. How many different orders are there? Listen. So you got to times by 2. Come on! 3 goes into 9 3 times, so the answer is 4 over 27. So easy. Okay, now what about this one? 1 of each color. Now remember, now we're pulling out 3 marbles. 1 of each color, so to do a specific case. Blue on the first, red on the second, green on the third. What's the probability of pulling out a blue marble on the first draw? 4 nines. Now, or put it back in the jar. What's the probability of pulling out a red marble? Okay, this is enough for this already. Let's turn this off. My arm is getting sore. Wow. Now pull out a red marble on the second draw. 3 nines. Put it back in the jar. What's the probability of pulling out a green now? 2 nines. But is that the only order you can get 1 of each color? No, you need to multiply by the number of orders, which we said before is 3 factorial, right? And then same thing here. Do a specific case. Red on the first, red on the second, green on the third. What's the probability of pulling out a red on the first? 3 nines. Put it back in the jar. 3 nines. Put it back on the jar. 2 nines. But is that the only order? No. How many different orders are there? So you need to multiply by 3. I will leave the computation for you. So, did you notice that in the first example I did, the second draw, that affects, well, whatever you did on the first draw affects what happens on the second draw, right? So that's why we have this. But when you do replacement, when you replace the marbles, then what you do on the first draw doesn't affect what happens on the second draw, right? What do you call it when this event doesn't affect this event? No, it doesn't affect. We call those events independent. That's a different word. So if 2 events are independent, then the probability of event A and B occurring is simply the probability of A times the probability of B. Because what happened on the first one doesn't affect the second one. But the main thing is you just multiply, because see, you just do this in your head, right? I mean, you just automatically do it, right? Right? If I pull out 1 marble, there's only 8 left, right? It affects what happens on the second one. But you just automatically do it in your head. The main thing is you know you need to multiply it. Okay, so let me see if we got any harder problems than that on the homework. So let's see. I think you guys can handle the rest except the birthday problem. Now I'm going to tell you right now, this birthday problem is going to be on the quiz and it's going to be on the test. So make sure you can do the birthday problem. Now if you were in my summer school class, I think I told you the birthday problem, yeah? What about it? What do you remember about it?
There's this many people in a room.
Yeah.
How many of them, or what's the probability that they have the same birthday?
Okay, something like that.
Something
Yeah.
like that. That's all I remember.
Okay, let's say we have a party right here. I don't know how many people are here. Let's just say there's 50 people at a party. Okay, you go to a party. What's the probability that at least 2 people share the same birthday? if you have 50 people at a party? Or what if you had 20 people at a party, or 100 people? What's the probability that at least 2 people will have the same birthday? Well, I'm going to teach you how to figure it out. Okay, from January 1st to December 31st, how many different birthdays are there? 365 or 366? Is it possible to be born on February 29th? Or not possible? Do we just discount those people? What, you're born on February 29th?
Yeah.
Okay, so then you know there's 366 different birthdays, not 365. However, the probability of being born on February 29th is not the same as all the other days, right? So we're just going to pretend it doesn't exist. Just to make the problem simpler, or unless you want to make it harder.
No.
Yeah, that's what I thought. Okay, so let's just pretend there is no February 29th. No, we're just pretending. We know in real life there is, okay? So there's 365 birthdays. Now, this is the kind of problem you see on the SAT. How many people do you need in a row to be absolutely sure at least 2 people will have the same birthday? You guys understand the question, first of all? How many people do you need to have in a row to be 100% absolutely sure at least 2 people are going to have the same birthday? The answer is 366, right? Because if there were 365 people in a row, isn't it possible everybody could have different birthdays? It's possible, right? But once you add one more person to that row, guarantee he's got to match up with somebody, right? Because there's only 365 different birthdays. You guys understand it? Okay, now let's answer the question. How many people do you need in a row to be like 50% sure at least 2 people have the same birthday? Or what about 90%? Or what about 99%? See, this is the difference between numerate and enumerate. The enumerate people are going to say, oh, 50%, just take 50% of that, 183. No, probability doesn't work like that. You don't. Or 99%, just take 99% of that, 363. No, it doesn't work like that most times. So I'm going to show you how to compute these probabilities. Okay, here is a row. Okay, now remember, there's 365 different birthdays, yeah? The first person enters the room. What's the probability that he has a birthday? Guarantee he has a birthday, right? So it's 1. Okay, but I'm going to write 365 over 365 because you're going to see a pattern. Okay, now, a second person enters the room. What is the probability that his birthday is different from this person? Okay, this person already got one of the birthdays. Just make up something, April 12th. What's the probability that this person's birthday is different from that one? 364 over 365, because this guy has one of them, right? So 364 over 365. Okay, now if I multiply these numbers together, what is the meaning of that? That's the probability that these 2 people have different birthdays. Third person enters the room. What is the probability that this person's birthday is different from the first 2? 363 over 365. You guys get that? Because these 2 guys already have 2 of the birthdays, right? So there's only 363 other birthdays. If I multiply those 3 numbers, what does that mean? That's the probability that all 3 of these people have different birthdays. Fourth person enters the room. What's the probability that his birthday is different from the first 3 people? 362. Do you guys see a pattern now? Tell me when you see the pattern so I can stop. If I multiply those numbers, that's the probability that all 4 of these people have different birthdays. Fifth person enters the room. What is the probability that this person's birthday is different from the first 4 people? Just tell me when you see the pattern. Because we're running on a board now because we're recording. If I multiply those 5 numbers, that's the probability that all 5 people have different birthdays. Just give me a nod or an animal sound. That was a llama. Okay, so this is the probability that all 5 of these people have different birthdays. So tell me, what are you going to get if you subtract it from 1? What is the meaning of that? That would be the complement of it, right? Like here, so what? Okay, if I roll a die, what's the probability that you're going to get a 6? 1/6. So if I subtract it from 1, what does that mean? That's the probability that you're not going to get a 6, right? It's the complement of it. You guys remember complement? Okay. Okay, so if I multiply these 5 numbers, that's the probability that all 5 people have different birthdays. If I subtract it from 1, you get the complement of that, which is, what's the complement of all 5 people have different birthdays? All 5 people have the same birthday? No, that's not the complement. See, you gotta know what the complement is. What is the complement of all 5 of these people have different birthdays? At least 2 of them have the same birthday. Because what if somebody said, all 5 people have different birthdays? What would it take to prove them wrong? All 5 of them have to be the same birthday? No, at least 2 of them have the same birthday, right? That's the complement. And there you go. So you can see that these numbers are hard to compute, so you do this on your calculator or computer or something, right? Okay. I'm not going to do anything until somebody computes. I'm going to turn it to period 3. Entertainment. Come on, you guys, iPad. You got the calculator on the iPad. Why you pull out a calculator when it's on the iPad?
Well, on my desk.
All you're going to do is punch it in and just like, try. Probably. It's got to be a number between 0 and 1, people. 0.027. Can somebody verify that?
Yeah.
At least pretend to punch something in on your iPad. Oh my goodness. You know, next week, I'm going to be filming this. You guys better be busy doing something. In fact, I'm going to call on you. I'm going to come up and then put, no, this is a project I'm working on, that's why. So I'm going to come up and I'm going to look at what's on your iPad and stuff. And then I'm going to ask you questions and then you need to respond, you know. Actually, it might be funny if you don't respond. So, psyched out. No, that would be funny. You just look into the camera. Just look into the camera, pretend that I'm not there. That would be funny. That would be hilarious. So if 5 people are randomly at a party, the probability is only 2.7%. At least 2 people are going to have the same birthday. And you can kind of figure it's low, right? Because only got 5 people there. But how many people do you need at a party to be 50% sure? Well, if you just keep on doing, like if you add a 6th person, what's going to happen? Then you just add the next one, right? Times 360 over 365. And you just keep on going. 7, 8, 9. So the first time this probability goes above 50% is when 23 people. You only need 23 people in a row, randomly selected, and the probability is 50%. At least 2 people are going to have the same birthday. See, the enumerate people think, oh, 50%. You just take 50% of that. You need 183 people in a row. No. You only need 23 people, and it's a coin flip. At least 2 people are going to have the same birthday. You guys don't seem impressed. And if you don't believe me, just multiply 23 of these, subtract it from 1. That's the first time it goes above 50%. What about 90%? Does anybody remember from summer school? I told you these numbers. 41. So if you have 41 of these, multiply them together, it's going to take a while. Subtract from 1. That's the first time it goes above 90%. Now what about 99? What did you say 99% is almost guaranteed? Yeah.
72.
No, you only need 58 people. 58 people in a row, then it's almost guaranteed. 99% is almost guaranteed. At least 2 people are going to have the same birthday. But a lot of people think, no, you got to take 99% of that. You're going to have 360-something people. No, because that's not how probability works. Probability works by multiplying things together. And when you multiply fractions together, it gets small very quickly. Now, we already did this in summer school. Remember we wrote all the birthdays on the board? Who was in my summer school class? Hanaoka? Well, you guys don't want to even admit, yeah? Okay, let's do this then. Let's do this. Now, of course, this is just probability now. This is not guaranteed stuff. So we got January, February, March. Is this the way to do it? April. Why do we even write it? Just write the month, yeah? January, February, March, April. Why am I putting the 0 before it? June, July, August, September, October, November, December. Whoop, 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 whoop. Okay, so when I call on you, you just give me your birthday. Like, here, I'll start it then. September 17th. Okay, start from yip and just come this way. Yip.
August 10th. January 5th. January 4th. July 25th. February 29th.
You don't exist. Next.
Oh, January 26th.
Okay, attention.
March 11th.
May 21st.
What?
May 21st.
June 29th.
January 18th.
January 1st. July 28th.
Is that it? Okay, but see, in this class, what, 4, 4, 4, I only got 13 people, including me, so the probability is not that high. But then when we add the other classes in, I'm pretty sure we're going to get a hit. Because you have 50, there's 50, how many people are in there? We're down to 54 in PC, no, we're down to 52 in PCH. So if you have 52 people, I would say the probability is going to be 98, 97%. That's still pretty high, right? Like if somebody told you the parachute opens 97% of the time, you would jump out of the plane, right? You think about that one. Anyway, this is the birthday problem. This is going to be on the next quiz. Except I'm not going to do the days of the year. I'm going to probably do days of the week. But since I told you that, I'm going to use the months of the year. The numbers are going to change. It's not going to be 365. Or maybe I'll say a planet only has like 10 days in a year. That way the numbers are manageable when you compute it. Do I have to show you the example? No, you guys, no. So you do tonight's one. I think tonight's one, who has the homework? I think tonight's homework is the days of the week.
Yes.
Is it?
Yes.
Yeah, so let's see if you guys can handle that. Okay, so the kinds of probability that we're doing is, we're doing like one at a time, right? You have marbles in the drawer, you're pulling out one marble at a time. There's an order to it. Okay? Now some of you are thinking, well, can't you just pull out all four marbles at once? Yeah, but then we're going to do that tomorrow. But the problem is, if the problem requires replacing it, then you cannot just pull out four marbles at once, right? Okay, think about that one. Oh, by the way, I think I told you in summer school, see, so now that you're numerate, you can make money off the innumerate people, right? Because on the planet Earth, probably what's the percentage of people that are innumerate? About 98% in the world. Yeah, so let's say you go to a party, you get 50-something people there. You know the probability is 99%, at least two people are going to have the same birthday. So you walk up to somebody, you just have a conversation, go, I'll bet you $20 that these two people have the same birthday. They go, no way, only got 50 people here. But you know for a fact it's 90-something%, right? So then you meet all the people and write down their birthdays, hey, it's got a match. You get earn $20. Now, of course, there is a probability that there's not going to be a match, right? But it's only going to be like 1%. So there is a chance you could lose. But so what happens if you lose? You go to another party. No, that's what you do. If you go to 100 parties, probably you're going to win 99 times and lose once. Of course, it is possible that you could lose all, but very improbable. You know what I'm talking about? So if you go to 100 parties, probably you're going to win 99 times and lose only once. So you're going to win, what is that, $980, and then you're going to lose 20, you made $960. Okay, don't then.
Have you ever done that at a party?
No, I did that at we had like a workshop. I forget what it was for, but it wasn't like math teachers, because math teachers all know this. Well, they should know. But we were in a school cafeteria, gosh. I don't know what it was for. It was some kind of conference. And there were like, it looked like about 50 or 60 people there. And then, you know how those conferences, they have icebreakers? You know what icebreakers are? So you meet, so that whoever was leading the conference, they said, okay, I want you to line up from January 1st of this side all the way to December 1st of this side. That way you gotta talk to people, right? You gotta ask them what their birthdays are, right? So they lined up, everybody, and as it turned out, there were like 7 or 8 people that match. Like 2 people born here, 2 people, and had 3 people born on the same day. And everybody's going, oh my goodness, this is incredible. The stars are aligning. No, and then, so after the conference, I wrote a note to the thing that said, if you have 58 people in a row, it's almost the probability is 99%, at least 2 people are gonna have the same birthday. It is not surprising. It's actually surprising if nobody matches up. You know what I'm talking about? I don't know if that person, you know how you evaluate the person at the end of the conference? Anyway, I wrote that to them. I probably just threw it away, because they probably didn't understand it. No, so when you have a group of people, the probability is pretty good, at least 2 people are gonna have the same birthday. As long as it's more than 23 people, because 23 people is just 50%. You know what I'm talking about? You wouldn't bet a lot of money on just tossing a coin, would you? That's 50%. But if the probability, it's just like on the SAT, right? If you can narrow down your choices, you should guess, right? Oh my goodness. Okay, we're done. We're done. You guys better perk up for next week. It's extended.